Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about synchronization hardware as a solution to the critical section problem. How the hardware instruction test and modify and compare and swap in different formats can address to the critical section problem. What are the advantages and what are the disadvantages of implementing those algorithms? Software-based solution to Peterson solution to a critical section problem was not adequate and not guaranteed by some operating system that it can be solved the critical section problem. Now, there are some hardware and software-based APIs that can be used by this most operating system to solve the critical section problem. They are available to the kernel-level developers and application programmers. Now all these APIs implement the locking protocol to implement these algorithms to solve the problem. That a process should acquire a lock before entering the critical section and it should release the lock after exiting the critical section. So we will now see that what is the general diagram of this critical section problem using locking. Here, acquiring lock is the entry section where it is actually requesting the permission to get entered into the critical section after the critical section is being executed. After the critical section is being executed, exit section is performed followed by the remainder section. So that is a general syntax of locking mechanism to imply on a critical section problem. Now today we will discuss about synchronization hardware solution to the critical section problem. We will involve simple machine level hardware instructions that can be implemented in the critical section problem. They are very implementing hardware solutions easy and reliable and that can also improve the system performance while implementing with the critical section problem. The critical section problem could be simply solved in a single processor environment where the interrupt can be disabled while the modification of some kernel data structure such as list of open files or memory management or interrupt handling. In this way, that only one process can execute and access the kernel data structure at a time, it will execute in the exact sequence that the data should be synchronized. As no other processes are following this process in the critical section, then no preemption is needed. It is followed by mainly the non-preemptive kernel to solve this critical section problem. But this is very difficult while implementing in the multiprocessor environment while different processes are executed and accessing the critical section while executing on different processor or available CPUs. Now in that case, we can use several hardware implementations to solve this critical section problem. Disabling multiprocessor interrupts can actually delay the time by the message is passed to be all to the processes and this message passing can cause delay in entering the critical section and it also makes an effect on the system clock which is kept updated every time the interrupt is happening. So that is why disabling interrupt is not a way to be done on the multiprocessor environment. Many computer systems provide this hardware implementation like they can test and modify often content of a word or swap the contents between two words atomically, that is one as an uninterrupted unit formed to the test and critical section problem. The critical section problem can be solved by these following processes. The first one is the test and modify, and the second one is the compare and swap method. First, we will define that how test and set function can be done with the shared data structures. This is the basic definition of a test and set function, which is a return type of boolean and also a pointer to a boolean variable known as target. Here target is tested and set to be modified with the new value. First the target is set to the false, and after that testing it will be done and reset to the value of true. And this value will be returned to the new function to enter the critical section. Now, the test and set characterized definition is said that the instruction should be executed atomically, as we say that as an uninterrupted one unit. Now, if two test and set instructions are performed executedly by two different processes onto different processors, then they are to be done in some arbitrary order of sequence. Now, if the test and set functions can be implemented and supported by the operating system, then they can be done using a global variable named as lock, which is then to be passed as a pointer to this test and set function and first initialized to false. Now, when we are passing the lock variable using this test and set function, it is actually returning the value true, which is the modified value. Thus, the process can enter the critical section. So, calling to the test and set function is actually in the entry portion of this critical section problem. After executing the critical section, now we are releasing the lock by setting it to false. Now when the lock is false, then any other process can call the test and set function to get in the critical section. And the remaining code is in the remainder section. So in this way, test and set function can be implemented to solve the critical section problem. Now we will see another problem or definition of function known as compare and swap, which are using the same global local variable lock, and thus the definition is all about the same with the test and set definition. Here the main function of the compare and swap function is to compare two values, and if they are required to meet the original satisfaction, then they will swap their actual contents, but will return the original value instead. So first we are checking that if the value is equals to the expected value, if it is equals to the expected value, then the new value is swapped with the original value. Regardless, the compare and swap will always return the original value of these variables. Now, this compare and swap, how we implement it, we will see that. Now compare and swap also execute the instructions atomically, and mutual exclusion is provided as follows. First, we have set the global log variable to 0, which is initialized. Now we are passing this log variable as an expected value of 0 and the new modified value as 1. So when we are passing the pointer to this log variable to the compare and swap function, it is actually checking that the value of log is 0 or not. If it is 0, then it is modified to 1 to let the process which has invoked this compare and swap function to enter its critical section. Subsequent calls to compare and swap function will not succeed because it will not let the value of log become 0, as if the value will be log is 1. As we know that compare and swap always return the original value of the variable, then it will return 1 in subsequent calls. Thus will not make every process to enter the critical section. So mutual exclusion is avoided. So after the process exits from the critical section, it will again initialize the log to 0, which will be considered at the exit section of this program. And as we know, the remaining portion is the remainder section. Now it has set the log to 0, so it is telling the operating system that other processes are allowed to enter their critical section now. Although these two functions that we have described are provided with the mutual exclusion, but they do not guarantee or satisfy the other requirements of progress and bounded waiting in the critical section problem. So we can implement test and set or test and modify in some other way to actually achieve those requirements set or met by this critical section problem. So we'll now see that how to do that. So here in the test and set definitions, we are actually sharing the following data structure. So these are the two data items that are shared while using the test and set function. The first one is used for n processes, which is a Boolean array named as waiting. This waiting Boolean array can actually store the number of processes waiting for the critical section to get entered. And the next local variable Boolean L, which used to determine that it is allowed to enter its critical section or not. Now to prove that mutual exclusion is required, so the PI can enter the critical section only if waiting I equals to false or key equals to I. Now this key I equals to false and waiting I equals to false can determine that PI can enter its critical section. To any other processes, waiting in the queue should be waiting J equals to true, that only one process can wait while PI is entering its critical section, thus allowing the next process to get in the critical section. So to do this, we are implementing this code. First, I is waiting for the critical section to get executed with the waiting I equals to true statement. The key is false at initialization, as we know, and the key will only get false when the test and set function will get executed. So the first process get executed will see that key is equal to false, as no other processes have executed the test and set function. And the other processes which are waiting in the queue thus can make them by clicking at true so that it can enter the critical section in next. So the mutual exclusion is proved here. So as we know that key only get false when the rest and set function is executed. So the first process, the key is true. Next we are checking that waiting I equals to true and key is also equals to true. Then the test and set function is executed using the global variable lock, which is initialized to 0. Now, after the test and set is returning, the key will be initialized with the return statement of this test and set function. So key will now have 1 as 0 is modified to 1. So now we are getting waiting I is equal to false, so the process I can get entered to the critical section by finishing its waiting for it. So all the sentences we have mentioned are in the entry section of this program. After that, I will get into its critical section and execute its code there. Next, we have to calculate that which is the process next to be calculated and executed in the entry section. So to prove that progress requirement is met, we take the applies to mutual exclusion variables, and again that waiting I equals to false that we have set and lock we have released so that the other progress can enter the rotating system, so that the other program can enter its critical section. Now the progress requirement is also set. Next we have to meet the bounded waiting requirement. As waiting I is equals to false and I has exited from its critical section, so we have to circularly check that which process is waiting for the next section to be entered to the critical section. Like from I plus 1, I plus 2, I plus n till I minus 1. In its circular way or cyclic way it is checking, and the first program or first process waiting in the queue should be given the critical section next. So that is why we are performing j is equal to I plus r mod n. So the next program with these n processes is stored in j. And if waiting I is not equals to false and j is equal to not I, then we are setting j is equal to j plus 1 mod n. Thus the next process waiting j to make it true. So now we are checking that if process I and j is equal to each other or not. If it is so, then we are setting lock equals to false. Otherwise, we are allowing the j to enter its critical section by making the statement that waiting j equals to false. So the remainder will be the remainder section in this program. So now any process j that is waiting in the queue should be turned now to the next critical section, and the other processes should meet their critical section requirement in n-1, that is n minus I, to get in their critical section. So this test and set and compare and swap function can be modified in this way to meet all the requirements of critical section. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.